Hello guys. So today in this video I shall talk about my interview experience at the Institute of Mathematical Sciences, Chennai. So last year I gave interview here for my PhD and applied, and IMSc is mainly it is IMSc actually is a research institution. It is based in Chennai. Actually it is under HBNI, and it is funded by DAE, Department of Atomic Energy. So if you know that DAE institutions are pretty much known for their good funding because uh, they give a contingency of amount 40,000 and which no one gives. Even if you qualified CSR net, they give you contingency near about 20,000. And in few IITs, if you join from the institute funded position, they don't even give contingency or HRA as far as I know. So, but DAE, if you join a DAE institution, either you are from CSR or maybe from institute funded, your fellowship will be good. And DAE institutions like other institutions like HRI, uh, TIFR, or maybe SINP, IOP, the Institute of Physics, so etc. These are all the DAE institution. So today I shall uh, discuss about the questions that were asked to me in my interview at the IMSc Chennai. So there were two people in my interview. One was Sitablu Sinha and another was Sankan Sharma. So they took my interview. So at first, I think they just wanted to know about my background, like from where I am and what is my interest in research. So this all that. So the Sitabro sir actually told me that I mean, he asked me that in which subject you are interested. So I said condensed matter physics. So he asked in Jadavpur, I mean, my MSc was from Jadavpur University. So in Jadavpur, who taught us condensed matter physics? So I said few of my professor's name, and he recognized one. And he asked me to say hi for him to my that professor in Jadavpur University at the start of the interview. So that was pretty cool. So uh, the professor was very much friendly. So at the initial stage, so this was the initial conversations. So I also said them when they asked me about my research interest or my MSc subjects that I read. So I told them nonlinear dynamics, solid state physics were my special topics. So Sita sir was is a genius people. I mean, he is now one of the famous researcher in the nonlinear dynamics area. So he told me that, so you studied nonlinear dynamics. So I said yes, and he asked me one of the basic questions in nonlinear dynamics. Even if you are not from nonlinear dynamics, you have not if I read that, it is not very hard to answer. So it is just a mathematics in just in a different way sense. So the first question was, you are given a plot d sorry, you are given an equation dx dt is equal to sin x sin x. So you have to find the uh, graph of x versus t plot x versus t. This is the first question. So what is your approach now? So you may try to find, like, do dx by sin x is equal to integration of dt plus some constant. Okay. So it is going to be cosec of x dx is equal to t plus some constant. Next, you can do the integration of cosec, find some log of something with t plus c, and then if you proceed in this way, you will see you will not be able to find x as a function of t. Sorry, because it is very hard to find, hard to find. And and if you try to do it in the interview board, so it is not they have not that much of time that you do the integration all these things and then find the plot. I mean, even if you find x as a function of t, the functional form will be so complicated that it will be almost impossible for you to plot. Okay, so let us try another method. Okay, so in interview board, I did not even go into this method because I knew from beforehand that this method is not going to work. So what I did was plot x dot versus x. Okay, so our equation was x dot is equal to sin x. It was our equation. Okay, so now let's plot it. So how the graph will look like? It's a sin x graph. Okay, so it's a sin x graph. So suppose the particle starts from here. Okay, say it is his x naught, initial x naught. At t is equal to 0, it is his position. So what will the particle do? And remember, the particle is moving in one dimension. It is only x. It is so in physically, it will move like this or this only in x direction. Okay. So here its velocity x dot is greater than 0. So its velocity is positive. So what should it do? Its velocity will increase in the positive x direction, right? Its velocity is positive, so its velocity should increase in the positive x direction. So it will go in this direction. Okay. So the particle will move from this direction, and when it arises at that point, what will be its velocity? Its velocity is 0. So the particle will remain at rest here. Okay. So the part if the particle starts from here, it goes from here and stops. So it is known as a stable point. Stable point because the particle is stable here. Okay. So take another point like here. What you now say? See what the particle will do. Here the velocity x dot is less than 0. Here x dot was greater than 0, right? So what will the particle do? It will go in the opposite direction now, and again it will come at this point and rest, right? So again take this point. What will it do? It will go in this direction now because x dot is greater than 0. So it will come at rest is this point. So like this, you can see that there are certain points like this and certain points like this, right? So these points are unstable points. Why unstable? Because so actually these are stable fixed point and it is unstable fixed point. Why fixed point? Because in these points x dot is actually 0. But why unstable? Because if you shift x from slightly from this position to this position, it will immediately go to the stable one, right? But if you are at the stable fixed point and if you shift from here to here, say you are from here, suddenly you go and you will again come back to the same position. So it is a stable fixed point because the particle always wants to come to this position, right? So what are these points? Actually, this is actually our pi, right? Pi. This is 2 pi. This is 3 pi, etc., etc. Right? So pi, 3 pi, these are stable fixed point, and 2 pi, 4 pi, etc. These are unstable fixed point. So see, only from the x dot versus x graph, you have uh, uh, bring brought so many things. That is the particle velocity. You know that after a certain time, the particle will always end up at this position only, pi, 3 pi, or 2n plus 1 pi. Okay, the particle can only go in this position. Okay, so I told him this thing, and he was very happy to know to see that I could answer this one. But the ultimate aim was to plot x versus t graph. So let me check if I've started the video or not. Yes, yes, I have started it. So now, how do you plot? Though actually in the interview board, I did not have to answer the plot to how to plot, because the plotting is a bit lengthy one. So as he under and he asked me other few questions from here too, because he asked me that if why the particle does not oscillate. So I can also say that the particle so it is like this. Okay. So can the particle oscillate, like it starts from here, here comes here, again goes to here, again comes here? Can the particle oscillate? So I said no. Oscillation is not possible in one dimension. Why it is not possible? Because see, the particle velocity here is actually zero, right? Oscillation happens when you take a simple harmonic oscillator. So after it, say the pendulum. Okay, pendulum is a one dimensional system, so remember. Okay, because it has 1 degrees of freedom. So when it comes to the middle point, it has some velocities. Okay, it has some velocity. And when it goes to the this point, it has acceleration which brings it to the which reverses its direction, velocity direction. But here is no acceleration. Here only x dot, only velocity. X dot is equal to sin x. No acceleration was working here, and x dot is actually zero here. So no acceleration is working on the particle. So uh, we can say that in one dimension oscillation is not possible. Okay, it is a general rule in nonlinear dynamics, but still you can explain it here. So I answered it. But you can plot the x versus t by simple observation. Though I he did not I mean he switched to another question before me answering this one, because he understood that I could answer, because I have read these things before. So so what is the x versus t plot? You can also infer it from the graph. Okay, so see, there are few points like pi, 3 pi, etc. You can mark them in this here. X is equal to pi, x is equal to 3 pi, 3 pi, pi, etc. Okay. So you see that it is our x dot, right? X dot, and it is our x. Say the particle x starts from here. I'm so x naught, or x naught is less than pi, greater than 0. So say it starts from somewhere here. Okay. What happens? Initially the particle is here, so there is a finite positive velocity, right? There is a finite positive velocity, so its velocity should increase. Okay, so remember its velocity will increase as it moves, right? As it moves along this line, its change x dot increases, so its velocity increases, right? So and so remember a situation where the velocity increases. A particle is free falling, so its velocity is like gt. So its x is equal to half gt square, sorry, half gt square, because here the velocity increases. Okay, so its graph look like some parabola, right? but here the velocity that does not increase linearly, but in this only almost this region we can say that it increases linearly for our sake. So actually it increases, this is the main point. So x will increase as this one. So x will initially increase as like this. Okay, exponential, sorry, t square. So some power law type increase. Okay, but at this point x dot is maximum. So th- the slope will be maximum. X dot means the slope of x versus t curve. This curve slope is equal to x dot. So at this point the slope is maximum, and after this point the velocity starts to decrease again, and at this point it is becoming zero. So what is the slope? The slope will start to bend. The curve will start to bend, and the slope will become zero at the as time goes to infinity, right? Because the slope is zero here, and you can easily see that the particles, if x naught is here, the particle's final position is at pi. Okay, so similarly you can, if you so I have taken this part of the graph. If you take this part of the graph and draw the similar things, you will find that it will go like this. Okay, so sorry, actually I made a mistake. Okay, so from 0 to pi it is like it will be like this, and say there is a point like 2 pi. Okay, so so if the particle starts from pi to pi, between pi and 2 pi, what will it do? It does not want to stay in 2 pi, right? So it will move away from 2 pi, so it will go like this. And if it starts above 2 pi, it will go like this. So the plots will look like this. So see, from some few simple arguments, we have plotted some complicated x versus t graph. We did not have to solve the this hazardous integration, but we have already found the x versus t plot. Though my plot is a bit dirty, but yes, schematically it will look like this. So barring this one, these were my first few questions. Okay, from the nonlinear dynamics part. So the second question is was very much tricky, and uh, so let me first state the problem. So he gave me a 6 by 6 matrix, 6 by 6 matrix. Okay, 0 1 0 0 0 0. Okay, then 1 0 0 0 0 0, then 0 0 0 1, sorry, 0 1, no, I think it was right, 0 1 0 0 0, and after it was 0 0 minus 1 0 0 0. The next one was 0 0 0 0 2 0 0 0 0 0 0 minus 2. So Sitabro sir showed me this picture of a matrix, this picture, that matrix picture, and asked me to find its eigenvalues, and vectors. So actually, I was completely blind. I maximum what I could do was solve a 3 by 3 matrix. But 3 by 3 matrix is the maximum that I have solved. I did not have any idea of how can I solve it 6 by 6. I cannot even go to a 4 by 4 matrix. So 6 by 6 matrix was a I was like, what is this? Can it be solved analytically? I was totally shocked. So, but he asked me few simple questions like, have not you seen this kind of matrix before? I said no, sir. So I mean, no, sir. I mean, I was feeling pretty bad that I mean, he was asking me like, have you read about block diagonal matrices? I said no, sir. I did not heard. So I was feeling pretty bad there. So okay. So but he was not very upset. He asked me to observe. He said, observe this matrix and say what do you notice. Okay. So I took my time. I took my time and looked at the matrices for a few moments. The first thing I said that, sir, this matrix is in a form where only the block matrices are there like this. Right, right. So I noticed this. Like there are no off diagonal elements. If we take a 2 by 2 form, if we take a 2 by 2 form of this matrices, they are only block matrices. So he was very happy first to know that. So okay. So now tell me what are the eigenvalues and eigenvectors. So I did not have any idea. So I gave him few hints like, sir, we find eigenvalues like eigenvalues. What is eigenvalues from a general rule is equal to um sorry sorry uh, determinant of a matrix, determinant of a matrix is equal to some sum over, sorry, it is it is the multiplication of all its eigenvalues and other few rules like a trace of a matrix is equal to sum over all its eigenvalues. So so I said that, sir, this condition is not going to help me because I don't even know how to find the determinant of a 6 by 6 matrix. But even this condition is not going to help me because there should be, I know that it is 6 by 6 matrix, so it will give us a 6 order 6 polynomial. So there will be 6 eigenvalues, but only one condition from one condition we can get from here, like from trace of this matrix we can see that it is 0. So only one condition I can get from here. So it is not going to help us very much. So what can I do? What can I do now? Do now? So he said me, you notice it is in a block diagonal form. So can you do anything from there? So I could not think that very much. But even at I mean I was almost going to give up. I mean nothing came to my mind. What can I do? But at the I mean he just I mean thought to change the question and go to another question. At the end moment, I just suggested him something that, sir, we can say the block 2 by 2 blocks as some say this block as x, this block as y, and this block as z. Okay, we take it as x y z. Some x y z are 2 by 2 matrices. Okay, and I said him that we take like this 0 0 0 y 0 0 0 z. We write the matrix in this form. Okay, now it is a now the matrix is in a form that is we know. I mean its eigenvalues, eigenvectors we know, that is 1 0 0 uh, 0 1 0 0 0 1. Its eigenvector we know. So if we write a equation like x 0 0 0 y sorry 0 y 0 0 0 z, and here is some eigenvector and is equal to lambda into something. Okay, so what will this will give us the condition like x of something 1 0 sorry x of the say it is a1 a2 a3. Okay, a1, so it will give us, so forget this. Okay. Say we don't know the eigenvectors. So this is general rule. Okay, a1, a2, a3. We put a1 as vector because it is a column. It is a column vector, right? Because it is a six. Actually, it was a 6 by 6 matrix. So A1 has to be of order 2 by 2, right? So you can write now x of A1 is equal to lambda of A1, right? And y of A2 is equal to lambda of A2, and z of A2 A3 is equal to lambda of A3, right? Now see that now my problem of 6 by 6 matrix has resolved into a 2 by 2 one, because it is a 2 by 2 matrix, right? We can always find its eigenvalues and eigenvectors, right? You can always find its eigenvalues and eigenvectors. So uh, so from here we can find the eigenvalues of x. X to be, what was x? X was our 0 1 1 0. X was 0 1 1 0. So I so you can find this eigenvalue. It is a 2 by 2 matrix, very easy to find. Similarly, you can find y as 0 1 minus 1 0, 0 1 minus 1 0. You can find its eigenvalues and eigenvectors. Similarly, write z as 2 0 0 minus 2, 2 0 0 minus 2. Find its eigenvalues and eigenvectors. Once you find a1, a1, a2, a3, and corresponding eigenvalues, so you can now simply say that, so it will have two eigenvalues, say lambda 1, lambda 2. It will have lambda 3, lambda 4. It will have lambda 5, lambda 6. So as the matrix is in a block diagonal form, so these will be our eigenvalues of these matrices only. So actually this will be our eigenvalues of this matrix. And what will be the eigenvectors? So the eigenvectors thing, I did not say that much clearly, that I will tell you now, because I was in a confusion then, because I just suggested him this idea. So and he was very happy that I could even say the I mean, when I say this part, he was very happy that okay, I understand. You have to. I think you can go from. So uh, I did not have to explain that much. So but now I am explaining it to you so that you can understand. So now you can find, if you can find a1, so one eigenvalue will be a1 0 0. So this 0 actually is 2 by 2 0 column. Okay, and this a1 will be a 2 by some number. Okay. So and another eigenvector will be 0 a2 0, another will be 0 0 a3. So this will be the answer of this question. Okay, it was I mean, it was not a pretty straightforward question, and but not too hard though. If you can think in the interview and suggest few ideas, it may work. Okay, so gone this question. Next, third question was from quantum mechanics. It was pretty easy question. So he asked me to find the ground state and first excited state of a infinite square wave to draw. So the first ground state was like this. The first excited state was like this. Sorry, was like this. So okay, done. Okay, so he just asked me to draw this. Then what he did was introduce a barrier like this one. Now he asked me to draw the ground state. So it was, so it is pretty clear. How will be the ground state? It will be like, okay, it will decay like this. So I drew that, draw that. So next he asked me, why did you draw that? I mean, explain me. It is correct, but I have to explain. You just cannot escape without explaining. Okay. So I said that, sir, in these places, the the particles, so if the ground state energy was like this, okay, it is the ground state energy not, and if this in these places the potential is greater than the energy, then the particle is very unlikely to be found here, so its probability should decrease. And but this is the first observation. Then he asked me that, so what is the what is the probability of here and here. So is it zero here? Is it zero here? So because the graph I had drawn that time, it was like very, I mean, it was almost becoming zero even before this. Okay. So he asked me, is it zero here? I said, no, sir, it will not be zero, but it will be very small, but it will be zero at the edge. It will be zero at this age, it will be zero, but here in these places, it will not be zero, but it will be pretty small compared with the other places. So he was said, okay, uh, and uh, and explain again and why it decays like that. Because there are many ways. If you just say the probability has to be small, it can decay in like many ways. Like you can decay it like you go 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 just linearly decay. You can decay like this also. So, but why it decays like that only? So why there is exponential decay? So I told him that, sir, the main idea behind the main concept of the wave function is it has to be continuous. So it has to go to zero. I mean, it's the wave function cannot be discontinuous. Okay, a wave function and its derivative cannot be discontinuous. Say we take a graph like this. Okay, say we take a graph like this. Okay, so here though the wave function is continuous, its derivative is not continuous. So this cannot be a option. So it has to go like its derivative and the wave function has to match at the both points and its derivative also. So the only option remains like this. Only it's the only option, and it can always decay like this because this is the only option remaining because the wave function and its derivative has to be continuous at these edges. Okay, so it was, I mean, he was very happy about this. So next he asked me, so suppose I build up a small, I mean, say its width is a. I'm sorry. Say its width is a. I make the width a very small and add very much number of steps in between. Sorry for the bad drawing. So now how the wave function will change? So it was pretty straightforward. We can draw conclusion from here. From here, that is the wave function will look like the same, but it will decay much before that because there was only two steps. Here there are many steps. It will decay much before that. Okay. So he did not ask any explanation of this curve. So I don't know if it was okay or not, but he did not ask me said anything. He just said okay. He asked the another person, the scientist sir, to ask questions. So this was his part, Sitar sir's part. So scientist sir asked me question that uh, he said sun. Okay. So here's in sun, what was the temperature around? I said around 5000 Kelvin. So at so much high temperature, why don't the particles in the sun? I mean, actually, so actually before asking this question, he asked me a few questions like solar wind. Say, he told me that have you heard about solar wind uh, uh, before? So I said, no, sir, I did not heard here. So he explained in short word that solar wind is a some wind of particles. I mean, a wind of solar particles of very high temperature, which sometimes goes over at some planet or something. Some wind of some high temperature particles, solar particles. So I mean, its origin is from sun. Okay, some particles of high temperature, its which origin is from sun. It's like a tornado you see in Earth. So it's like that. So it's a wind. Solar, it's named solar wind, but it's like this. Okay. So so there are few things like solar wind. So you know that suns. So the first question was actually uh, why the particles in the the temperature of the sun is very high. Okay, so why the particles in the sun, why particles in sun does not escape, does not escape. So it has very simple answer, but I at the time of interview I was very much uh, I thought that if he has asked a question, so it may have some deep inner meaning. So maybe I have to think a lot. So I gave some foolish answers before. Like said, I also said that the particles is has some very high velocity, so its mass will increase. So I mean, some ridiculous answers. So after giving few ridiculous answers, at the end of the day, I said them, sir, okay, sir, only there is a gravity of sun. So there is a thing called gravity. So the gravity don't let the particles go away. So he said, okay, okay. So next he said that, so what about solar wind? Because in solar wind we see that few particles are always escaping. So why then? What is the origin of solar wind then? So I said that said the temperature we are talking about, this temperature, this T is equal to 5000 Kelvin. Where do we get this temperature? It's an average temperature. It's an average kinetic energy. It's an average kinetic energy of the particles in the sun, right? At the surface of the sun. So it's not necessary that all the particles in the sun have this temperature or this energy. It may happen that few particles have less energy and few particles have much higher energy than that. Okay, so what actually happened that the gravitational energy of the sun and the kinetic energy of the particles, they both cancel each other. So I mean, by kinetic energy the particles wants to move away from the sun, but the gravitational energy holds it on the surface. But it's not for all particles. So few particles can have much higher energy or energy than kinetic energy than this average temperature. So its corresponding energy is kBt. So he said that how do you know that how much number of particles should have this number of should have much higher energy? What is the actual number? What is the actual quantity? How do we measure that? So I said him the famous Maxwell-Boltzmann distribution. So he asked me to draw that. So I draw it like this. So sorry, at the time of interview, actually, what I did was draw it like this one. Okay. So my drawing was very bad. So he was confused and he asked me why it is symmetric about this. Why it is symmetric about this point at the maximum point. So I said that it should not be symmetric. But he said that you have drawn it at symmetric. So I said no, sir, it should not be symmetric. So I removed that one and again plot it like sorry. I'm I'm again plotting it in a bad way. So it's not a very good plot, but still I think you can understand. Okay. Why it should not be symmetric? Because see it starts at zero. It starts at zero and it ends at e tends to infinity. Right? So and there is a maxima in between. So if it has to it could have symmetric that the I mean for a symmetric function what happens? For every plus m there is a minus m also, right? But here is no negative thing, no negative. So it cannot be symmetric. It cannot be a symmetric function. So and there is a maxima in between. So and okay, it may have symmetry about some other points, but even if you go any other point, there is a cutoff zero. It cannot be symmetric. Okay, like if you draw any function like this, which starts at zero and ends at infinity, it cannot ever be symmetric. But yes, but if your function is like this, that is, it starts at zero. It's falls at, it's actually start, it's not a Gaussian function, it starts at 0 and falls at some x naught, then it is symmetric about x naught by 2. It exactly falls at x naught, it's not a, so it is symmetric, but this is not symmetric. Okay, so he told me describe this graph, why it happens. So why it is like this in this region. So I said that the function was like f of p some constant, was some constant v square into j minus p square by 2 kbt, right? I think it was the distribution, Maxwell-Boltzmann distribution. So what happens here? So when v is small, so energy is very small, we can expand it like 1 minus v square by 2 kbt plus blah blah something. Okay. So the first term is v square. So it will always go as v square here. Okay. And then you can find a maxima and do all the all kinds of stuff. Okay. So actually, so what happens for the solar wind? There is the average energy. It is around kbt is equal to, sorry, some t is equal to, sorry, not kbt. Yes, it is here E equal to kbt is equal to 5000 kb. Okay, this is the average energy, but the particles which are in this region, okay, they have energy much higher than 5000 kb, right? So they can always escape. So this, and number of these particles obeys the Maxwell-Boltzmann distribution. Okay, so that's all. That was the only four question. My interview was not very long. It was around 30, 35, 30 to 35 minutes maybe. So it was not very long interview. So and yes, so these are all the questions they asked, and yes, I was finally selected at the IMSc. So I mean, actually, what I did not even know if I answered it, because most of the questions were not that you know from beforehand, and you go and answer, and sometimes you don't even know that if you have answered it right or wrong, and usually what happens that they take long interview of students whom they want to take, and my interview was very short. I heard many of my friends who have given interview like 1.5 hours to at the IMSc, because the interview, the interviewers come there with their time, they take long interviews too. My interview was short, but they don't take long interviews too, when they try to take understand the candidate very well. So uh, so after so I was finally selected at IMSc, and as you know probably, and I am now continuing my PhD here. So these are the all questions from my questions and interview experience. And yes, at the end of the interview, the Sitar Prasad again told me that don't forget to tell a hi to your sir, professor at the Jadavpur University. And later I told my professor at the Jadavpur University that Sitar Prasad gave you a hi from his side. And he told me that they both were colleagues. They worked at the SN Bose for some biophysics work. So yes, so that is my interview experience. Hope you liked it. If you have any questions, you can ask me, and I will come up with my interview experience at other places too. So this is the first one, and there are and many more videos are going to come of my interview experience in different places. Okay, so goodbye. Take care.